With projections, the main idea is that you have some vector that's not part of a subspace, and you want to create a new vector that is part of the subspace and is as close as possible to the original vector. Like, for example, let's say your subspace is a plane. Let's say you've got a plane, and let's assume that this plane goes on forever in all directions, at least two-dimensionally. So maybe the XY plane, for instance. And then let's say we have a vector that's not in that plane. Let's say we've got a vector, let's call this vector U. And let's call this subspace S. What we want to do is we want to create a vector in subspace S that's as close as possible to vector U. And geometrically, how would we do that? What would it look like if you wanted to create a vector in subspace S, in the plane, that's as close as possible to vector U itself? Geometrically, how would you create that? Or how would you draw it? Like, I could draw out any number of vectors that are in the plane. But how would I specifically draw one that is as close as possible to vector U? Where should that be? Which direction should it be pointing? Like, if I start off with vector U, I want to make a new vector that's in S, but as close as possible, right? So if you imagine sort of vector U just dropping straight down, making a new vector in the plane S. Let's call this new vector P for projection. If we traced out the difference between those, what angle would you expect that difference to make with the plane itself? Yeah, this should be a right angle. So one way of interpreting this idea of projection geometrically is we're taking some vector that's not in the subspace and we're dropping a perpendicular. Create a perpendicular line between the tip of the vector and any point on the subspace. And then the vector we're looking for is from the beginning to the intersection of that perpendicular and the subspace. So this is sometimes referred to as dropping a perpendicular, in the sense that if you imagine the plane is horizontal and the vector is somewhere above it, we're just dropping straight down. And of course, it doesn't have to be down. This could be any direction. Maybe you have a vertical plane instead of a horizontal plane. Or maybe it's not even a plane. Maybe you've got a line, maybe you've got a three-dimensional subspace of a five-dimensional universe or something like that. The dimensions don't really matter here. The important thing is we have a vector that's not in subspace, and we're creating a new vector that is in the subspace, but is as close as possible to the other vector. If we had chosen any other vector, like let's say we had chosen a shorter version of this, then the distance, the error vector, would be longer. It'd be further away from the original vector. You could also think of this almost like casting a shadow. Like if you imagine there's some light source shining light straight down onto the plane, specifically beams of light perpendicular to the surface itself. The projection is just the shadow that this vector casts on the plane. So this is another good way of thinking of a projection. A projection is like a shadow that the vector casts on that subspace. You could even look at this in terms of components. You could think of vector U as split up into a component parallel to the plane and a component perpendicular to the plane. All we care about is the parallel component, the component in the plane itself. Any other questions on the geometry of that? And the terminology we're going to use here, by the way, we would say that this projection vector, we're going to call that the projection, and we're going to use essentially function notation here. The projection of the original vector u onto the subspace S, and we'll use S as a subscript here. The idea is that projection onto S is a function. Vector u is the input of that function, and vector p is the output of that function. So projection onto S is a function that takes any vector as input and gives you a vector specifically in set S as the output. And we would read this as the projection of vector u onto subspace S. So projection onto subspace S is the function. Vector u is the input, and vector p, the result, is the output. Any questions on that notation so far? Then let's try out an example. Let's start off with the simple case where instead of having a plane, we just have a line that we're projecting onto. So let's say we are looking at maybe a two-dimensional universe. You have a line L, and you have a vector that's not on line L. So let's say this is vector u. And of course, line L can be defined based on a basis vector. Any subspace can be defined based on a basis. For a line, how many vectors would be in the basis? How many vectors are needed in order to span a line? Yeah, just one. A line is one-dimensional, and we say it's one-dimensional because we only need one vector to span it. So let's say we have a vector in the line. Let's say this is, let's call this vector v1. If this were like two-dimensional subspace, we'd use v1 and v2. But let's say v1 is the only vector that's needed to span this line. So v1 is a basis for line L. So v1 is a basis for subspace L. And we want to take vector u and project it onto that subspace. And to do that, geometrically, we're just going to drop a perpendicular again. So if you draw out a perpendicular, the projection vector is going to be this. And we would write that as the projection of vector u, and we could say onto line L. But since it's one-dimensional and spanned by just one vector, we're often going to write this as the projection of vector u onto v1. That is, onto the direction established by vector v1. So formally, this is the projection of vector u onto line L, which is the span of vector v1. But we can just describe it as the projection of vector u onto v1, or onto the v1 direction. So vector u is the input that we want to flatten onto this line. v1 is the direction that we're defining the line by. That we want to flatten vector u onto the v1 direction. And notice that this forms a triangle. Geometrically, we've got this triangle where vector u is the hypotenuse, vector p, the result we want, is one of the sides. And then the other side is just this extra difference term. This is sometimes called the error vector. In the sense that if you treat vector p, the result, as an approximation of the original u vector, they're close, but they're not exactly the same thing. And this perpendicular line here represents how far off your approximation is, how much error there is in that approximation. So that's and that can be treated as a vector also. You can say this vector is the E vector, the error vector. In fact, we could say that the projection vector plus the error vector equals the actual vector U. So if you think of the projection as an approximation, this error vector is how bad of an approximation it is. A small error vector means it's a very close approximation. Any questions on that so far? Then let's use a bit of geometry here. Let's say we have an angle. Let's say we know this angle is, let's say we call this angle theta. So theta is the angle between vector v1, defining the direction of the line, and vector u. If you had u and v1's coordinates, how would you find that angle? How do we usually calculate the angle between two vectors? Do you remember how that relates to dot product? If you calculate, for instance, vector u dot vector v1, you can always calculate that by components, like x times x plus y times y plus z times z. But how does that relate to the angle between the vectors? Or to put it another way, when would you expect the dot product to be 0? Yeah, if the vectors are perpendicular, then u dot v is 0. Whereas, what if they're parallel? If the vectors are parallel, what would that tell you about the dot product? What sort of value would you expect from the dot product if they're parallel? Like if u and v are in the exact same direction. You specifically get 1 as a modifier, but the actual dot product is going to be 1 times their magnitudes. So you'd have u dot v would just be magnitude of u times magnitude of v times 1, no further modifier. And what's a trigonometric function that does this? What trigonometric function is 0 when the angle is 90 degrees and 1, the largest, when the angle is 0 degrees, when the vectors are parallel? Yeah, cosine. In fact, u dot v can be written as magnitude u times magnitude v times cosine of the angle between them. That way it turns into 0 when they're perpendicular because cosine of a right angle is 0. And it turns into just magnitude times magnitude when they're parallel because cosine of 0 is just 1, the largest it can be. So in general, a vector dot a vector, any dot product can also be written as magnitude times magnitude. And I'm just going to write the magnitudes as the variables without the vector signs, because writing out these double absolute value bars gets pretty tedious and makes the equations look pretty cluttered. So when I write u and v1 without the vector sign, that just means the magnitude of those vectors. So vector u dot vector v1 is going to always equal magnitude of vector u times magnitude of vector v1 times cosine of the angle between them. And that means we're getting somewhere. We can figure out that angle based on the dot product. Also, though, in a right triangle, what does cosine mean? What's the usual ratio that cosine represents in a right triangle in basic trigonometry? cosine equals which side over which side? Yeah, adjacent over hypotenuse. And the adjacent side here is the projection, at least magnitude of the projection. So if we make that substitution, we've got magnitude of u times magnitude of v1 times cosine, that's adjacent over hypotenuse. Adjacent over hypotenuse would be the projection vector as a magnitude divided by the hypotenuse as a magnitude. So vector u dot vector v1 is going to equal magnitude of u times magnitude of v1 times magnitude of the projection divided by magnitude of u. And what happens when we actually multiply that out? What can we simplify there? Yeah, magnitude of u and magnitude of u cancel out. So that means when you take the dot product of u dot v1 as vectors, the resulting scalar is magnitude of the projection that we're looking for times magnitude of vector v1. And we can then solve for at least magnitude of the projection by saying magnitude of the projection, just divide by magnitude v1. Magnitude of the projection is going to be u dot v1 divided by magnitude of v1. That at least tells us how large the projection is. Any questions on the geometry there so far? Of course, a vector needs magnitude and direction. So if we really want to write out vector p, we need to have a direction as well. However, vector p should be in the same direction as what other vector? Vector p is in the same direction as, yeah, same direction as v1. So we should be able to just write vector p as vector v1 times some modifier. So v1 establishes the correct direction, and we need a multiplier that will give the magnitude of this. However, we can't just use this as the modifier on its own, because this is the magnitude we want. If we just multiply the magnitude we want times the vector in the correct direction, then this is going to influence the magnitude. Like let's say v1 has magnitude 3. We take the magnitude we want, we multiply by v1, we now have 3 times too big of a magnitude. How do we correct for that? How do we prevent magnitude of v1 from acting as an extra multiplier that we don't want? That'll just make it too big even more though, because we already have an extra times v1 that's going to be too much in terms of magnitude. If we also multiply by magnitude of u, that'll be too much by even more. How do we get rid of, like let's say v1 happens to be magnitude 3. That means this formula will give us a vector 3 times as big as we need. So how do we cut it back down to the right size? If, for instance, we've got an extra times 3, how do we get rid of that? What's the opposite of an extra times magnitude v? Yeah, we just need to divide by magnitude of v1. So if we have divided by magnitude v1 again, that cancels out the extra influence from the size of vector v1. In fact, if you take a vector and divide by its own magnitude, what does that produce? Anytime you take a vector and divide by its own magnitude, yeah, you get a unit vector. v1 divided by its own magnitude, that is a unit vector, a vector whose magnitude is 1. in the direction we want. So this is actually a very convenient way of building a vector. You take a unit vector in the direction you want times a scalar representing the magnitude you want. So in much the same way that you can write a vector in terms of its XYZ components or whatever components are needed, you can also write a vector in terms of magnitude and direction. The magnitude is a scalar multiplier. The direction is represented by a unit vector in the direction we want. So this should give us P, the projection, as a vector. And we can combine these a little bit more as well. That might be more convenient. If we take this magnitude V1 and bundle it into the denominator of the other fraction, we get V1 times U dot V1 divided by magnitude times magnitude. But what do we call the magnitude of a vector times itself? How do you usually calculate magnitude of a vector anyway? Like if you have the components of a vector and you want to calculate the magnitude, how would you do that? I mean, ultimately, we just got magnitude V1 squared here, right? But how would you actually calculate that? What's your usual procedure for finding the magnitude of a vector? If we go all the way back to the dot product formula, we were saying earlier that U dot V is U times V times cosine theta. What happens if you take the dot product of a vector and itself? V1 dot V1, it is related to the Pythagorean theorem, but we can write it in a more useful way for vectors specifically. V1 dot itself, we're going to get V1 magnitude times V1 magnitude again, times cosine of, what's the angle between a vector and itself? Yeah, cosine of 0 degrees. Cosine of 0 degrees is 1. So we get V1 dot itself equals magnitude times itself. So that's just magnitude squared. In other words, if you want to find the magnitude of a vector, you can just take the dot product with itself and then take the square root. And this does result in the Pythagorean theorem if the vector is, if you're writing out the dot product with the usual components. Like if you've got a vector that looks like x, y, then that vector dot itself would just be x times x plus y times y. X squared plus y squared in a square root. But it's very convenient to write this in terms of a dot product because that means magnitude of V1 squared is literally just V1 dot itself. So this gives us a very convenient formula for the projection. If you want to find the projection of an input vector u onto a line spanned by the direction vector v1, you just take v1, because that's the direction you want, times this ratio that gives you the correct magnitude. And this ratio is the dot product of the input vector dot the target direction divided by the target direction dot itself. The u dot v1 takes into account the angle because u dot v1 involves the angle. And the dividing by v1 dot itself is essentially to prevent v1's own magnitude from making a difference. Because v1's magnitude shouldn't matter. If we had used a v1 in the same direction but a different length, we still want to get the same value for p. We still want the same projection vector. So the v1 dot itself here, the denominator there is largely just to prevent the size of v1 from making any difference. But this is our typical formula for projection of v1 or projection of u onto v1. Vector v1 to establish direction times this ratio to establish the correct size. So this formula should generally work anytime you're taking any vector and projecting onto the direction of any other vector. In other words, projecting onto any one-dimensional subspace. And order doesn't really matter here. Dot product is associative and commutative, so you can change like u.v1 could be written as v1.u without changing the result. And since this is just a vector times a scalar, it doesn't really matter if we write that scalar on the left side or right side of the vector. If we're dealing with matrices, then order matters a great deal. But for dot products and scalar multipliers, order doesn't matter. Any questions on that formula so far? So let's give it a try. Let's actually throw in some numbers here. So let's say we have a vector 3, 1 that establishes a line. And we want to project another vector onto that line. Let's say we have the vector let's say 5, 3. Or 5, 4. And what we want to do is project vector u onto the line spanned by vector v1. So let's try that using this formula. The projection of the vector 5, 4 onto the direction spanned by the vector 3, 1. So we can start by just writing out the formula exactly as is. We've got vector v1. And note that the names don't matter. The important thing is that if you think of this as like input and target, we've got input dot target over target dot itself as a ratio times the target vector, because the target vector establishes the direction we want. So target vector times the ratio of input dot target over target dot itself. So let's work out each of those dot products. Five, 4 dot 3, 1, what's that dot product going to be? Yeah, 5 times 3 plus 4 times 1, 15 plus 4 is going to be 19. And then the denominator, 3, 1 dot itself. So that's just the magnitude squared of v1. 3, 1 dot 3, 1 would be how much? Yeah, 3 squared plus 1 squared is 10. So that means our result is just going to be 1.9 from 19 tenths times 3, 1. Or multiplying that in, 1.9 times 3 would be 5.7. 1.9 times 1 is 1.9. So that's the result. The projection is going to be 5.7, 1.9. So if we try drawing that on the graph, 5.7, 5 and about 2/3 of the way to 6, 1.9, something like that. So this would be our projection vector. And note that that is just the u vector flattened onto this line, with this as the error. Error in the sense of how far off our approximation is. If we use this projection vector as an approximation for vector u, we're only off by this much. Any questions on that so far? So this formula should generally work anytime you want to project any vector at all onto any straight line, any subspace, any one-dimensional subspace, spanned by just one vector. However, running this process over and over again can be kind of tedious. There are many situations where maybe you've got like one line, but you have lots of vectors you want to flatten onto that line. So it can be tedious to run these dot products over and over again. Instead, it's very useful to set up a projection matrix, which is basically just one matrix acting as an elementary well, not an elementary transform, but a matrix that acts as a transform to turn any vector into its projection immediately. And it can be kind of tedious to set this up, but it can be very worthwhile if you've got lots of vectors you want to project onto the same subspace. You just find this projection matrix once, and then you can multiply it by any vector you want to immediately get the projection. And one way to do that is to rearrange the terms in this formula to turn it into a matrix. First of all, have you seen how a dot product can be written in terms of transposes? Like if you've got a vector A dot a vector B. Let's say these are both 3 by 1. Can we just think of that as matrix multiplication? Vector A as a matrix times vector B. Can a 3 by 1 matrix be multiplied by a 3 by 1 matrix? No, and why not? Why can't this just be treated as ordinary matrix multiplication? Why would this matrix product not be defined? Yeah, the 1 and the 3, those don't match up. In order to multiply two matrices together, the inner dimensions have to match up. But we can modify this. How can you change vector A from a 3 by 1 matrix into a 1 by 3 matrix? How can you switch the dimensions? What procedure can you do to a matrix that swaps the rows versus the columns, the height and the width? Yeah, if we take the transpose, A is a 3 by 1 matrix, it's a single column, but A transpose would be a single row. A transpose is a row vector. Instead of 3 by 1, it would be 1 by 3. Now the inner dimensions match up, meaning that these can be multiplied. And what would be the dimensions of the result? Yeah, it would be 1 by 1. In other words, a single number, which is exactly what a dot product is supposed to be. So this is another way of writing the dot product. Any dot product can be written as the first vector transpose times the second vector exactly as is. And by writing it as a matrix multiplication, that means we can apply any principles of matrix multiplication we already know, any properties we already know, any useful shortcuts. It's very useful to be able to write it as a matrix multiplication problem. And there are actually two ways we could do this, because we transpose the first one to not only make the dimensions match up, but to make the result 1 by 1. So if you take vector A and vector B, transpose the first one and multiply, the result is just A dot B. However, if we transpose the second one instead, let's say we take vector A, which is, let's say, 3 by 1, and take vector B, but transpose it, now vector B would be 1 by 3. Can those be multiplied? Yeah, these can be multiplied because the inner dimensions match up. 1 and 1 are the same. But the result's not just going to be a single number. What sort of result would you expect here? Right, you're going to get a 3 by 3 matrix. So there's two different ways of doing this. If you take the transpose of the first vector times the second vector, the result is just a single number, which is the dot product. If instead you take the first vector as is times the transpose of the second vector, instead of getting a single number, you get a square matrix, n by n. In this case, 3 by 3, but whatever size the vectors are in terms of number of components. So generally an n by n square matrix. So there's two different ways you can combine vectors using transposes like this, transposes and ordinary matrix multiplication. These are typically called the inner product because we're putting the transpose on the inside, and the outer product because we're putting the transpose on the outside. So if you see the term inner product of two vectors, that's basically just another word for dot product. It's a little more generalized. There are some situations where you're dealing with other kinds of vectors where dot product is not defined, but you can define an operation that acts like dot product, and that's usually still called the inner product for that vector space. The outer product, on the other hand, takes two vectors as input and gives you an n by n square matrix as output. So these are two different ways of combining vectors. They're very closely related because they're both just taking the transpose of one of them and then multiplying as matrices, but they give you very different sorts of results. Inner product gives you a single number, which happens to be the dot product. Outer product gives you a square matrix. Any questions on that so far? So with that in mind, let's try rewriting these dot products. One thing I'm going to do first, I'm going to swap the order of the numerator. We've been writing it as u dot v1, but like I said earlier, we can change the order of dot products and the result is still the same. So I'm going to write this as v1 dot u. And the reason I want to do that, ideally, since u is the input, I'd like to be able to split u out entirely. So we just have a whole bunch of stuff times vector u. And that whole bunch of stuff is everything involving v1. So we're basically splitting this formula up into the stuff with v1 and the stuff with u. So let's try rewriting that in terms of inner products. We've got v1 times, and here we've got v1 dot u. So we can write that as v1 transpose times u. And now this is no longer a dot product. This is just straightforward matrix multiplication. The matrix v1 transpose times the matrix u. And likewise, this we can write as v1 transpose times v1 itself. And this is a little shaky because v1 transpose times v1 is going to be a 1-by-1 matrix. And you can't really divide by a matrix. But we can still treat this as this is just really a number, so we're just dividing by that number. However, if you take a look at the numerator, we now just have a matrix times a matrix times a matrix. And matrix multiplication is not commutative. We can't change the order around, but it is associative. We can choose which pairs to multiply first. In this case, we were thinking of it as multiplying v1 transpose times u, but you could shift the parentheses. What's v1 times v1 transpose? If you got a column vector times a vector transpose, what do we call that? That's not just going to be a single number, right? What is that going to be? It's going to be a matrix. It's not going to be the identity matrix, but it is going to be the outer product that we were just looking at. Because V1 times its own transpose, let's say V1 in this case is 2 by 1. Its transpose then would be 1 by 2. The 1's matching up means these can be multiplied. The 2's mean we get a 2 by 2 square matrix as a result. And that square matrix is the outer product of V1 and itself. So if we split that out, we've got V1 times V1 transpose. That's an entire matrix divided by V1 transpose times V1. That's just the dot product. That's a single number. And that whole thing multiplied by vector U. But this whole thing is a matrix. V1 times V1 transpose gives you a square matrix, in this case 2 by 2, because it's a two-dimensional system. Dividing by a scalar, it's still going to be a 2 by 2 matrix. So this whole thing is a 2 by 2 matrix that we're going to call capital P, specifically capital P sub V1. And that is a projection matrix in the sense that this matrix can be multiplied by any input vector, and the result will be the projection onto that space. For example, let's try this out. Using the same 3, 1 vector. If you want to calculate the projection matrix for the vector 3, 1, we can use this formula, V1 times V1 transpose divided by V1 transpose times V1, which is really just the dot product. So we take V1 times V1 transpose, in other words, 3, 1 as a column times 3, 1 as a row, and then divide by, and this one we can just treat as the dot product. 3, 1 dot itself. The dot product we calculated earlier was 10, so we just have 1 over 10 times a matrix. And that matrix is going to be 2 by 2. We're going to take every possible row of the first and every possible column of the second. So for example, if we take first row, first column. First row and first column is just 3 times 3, so that's 9. Up here, we're in the first row, second column. So we'll take first row, second column, that's 3 times 1. Down here, that's the second row, first column. So we'll take the second row, first column, 1 times 3. And lower right here, that's the second row, second column. Second row, second column. So we'll take second row, which is a 1, second column, which is a 1. 1 times 1 is 1. So this matrix is the outer product of V1 in itself, V1 times V1 transpose. And then, of course, we've got 1/10 times that. So matrix P sub 3, 1 is 0.9, 0.3, 0.3, 0.1. So that is the projection matrix representing projection onto that line. The idea is you can now multiply this matrix times any input vector, and the result will be the output, which is the projection onto that line. You can try that with 5, 4. Multiply this matrix times 5, 4. You should get the 5.7, 1.9 vector we found earlier. But the advantage here is that after you've done all the preliminary work to find the projection matrix once, you can now use this projection matrix to take any vector and project it flat onto the surface. So you're basically investing a lot of work early on, and in exchange, you save a lot of trouble later. So this idea of making a projection matrix is especially useful if you're going to be projecting lots of input vectors onto the same subspace. And also you can make variations of it for 2-dimensional and larger subspaces. The dot product formula only really works for a 1-dimensional subspace, a line spanned by 1 vector. But this formula for a projection matrix, there's a variation of it that expands it to 2-dimensional or larger subspaces. So you create a projection matrix for that subspace, and then you can multiply it times any input vector you want. Any questions on that? All right, then we can look at some more examples and expand this to two-dimensional subspaces next time. I will see you then. You're welcome.